Alrighty, it is 2 weeks since I was down in Louisiana working with Soundly at Little Tensas Bayou and Lake Pontchartrain. Did I have that right? 2 weeks? Yeah. Last week we did a hangout on Soundly's channel to just go over the results or talk about what we did. This presentation, this video is going to be a little bit more in-depth discussion or presentation of what I did at Lake Pontchartrain. So this is the geodetic triangulation to position the Marriott Hotel, performed on December 10, and I'll go ahead and get started here. There we go. All right, so you may have seen this before. This is just a tabulation of the results of the computed positions. The first column are the point numbers, as I called them. LP1 through LP4 are control points that I established from which to locate the Marriott building, and M1 through M6 are those points, being some roof corners and some red lights on the side of the building facing the lake. And what we have are the latitudes, the longitudes, and the elevations referenced to the North American vertical datum of 1988. And the latitudes and longitudes are on the latest realization of NAD 83, the adjustment of 2011. Now, the topic or the discussion in this presentation will not involve all of the computations. Maybe I could take the time to put together a presentation on that in another time. This one is going to be more about what was done for the work, to do the work, accomplish what was done. So here's a view out of my window on the 15th floor of the Marriott building, looking at Lake Pontchartrain. And this is just a snapshot or posting I made to my Facebook group called Flat Earth Can't Geodesy. I periodically throughout the day made postings to let people know what was going on and try to keep people updated on the progress of the work. Here's an overview from Google Earth, just showing you the points on the North Shore and the points on the South Shore. Let's take a closer look. Here on the right is the baseline established to do the triangulation from, LP1 and 2. And over here on the left is the Marriott building. From points 1 and 2, I triangulated to the corners and the red lights. Here's just a close-up of those positions as they were computed and how they land in Google Earth. On the North Shore, the baseline is LP3 and 4, and from LP3, I observed the Marriott building. Now, whenever I show pictures, and by the way, in this presentation, I'm going to show you pictures through my telescope of the Marriott building. But I want to discuss something beforehand. When I show pictures like this on Facebook or post or the videos that I make showing this type of information, there's a lot of criticism about surveying is affected by perspective. There's something wrong with these photos. This does not show curvature. A lot of criticism is being made about these photographs. Here's the Empire State Building. The one on the left is the city of Philadelphia. You could do this in anywhere where you can get some distance out to some prominent feature on the landscape or building or mountaintop. you can do this. You can take a theodolite, set the telescope to be horizontal, and look at where that crosshair intersects whatever land feature or building or whatever it is you're looking at, see where it intersects it. But again, we get a lot of criticism about that there's something wrong with this. And how can there be anything wrong with it? I mean, what possibly is wrong with this? I don't get it. In fact, over here on the right, the Empire State Building is a triangulation station. It's a third order triangulation station. It was intersected long ago to compute its latitude and longitude. So the reason I'm bringing this up now at this point in the presentation is to just make mention that the very methods that were used to triangulate and position buildings and position land features and create maps are the same methods I'm using that you're going to see in this presentation. And these are old methods. So I'm not making this up. This isn't something I've come up with. It's not, it's not mine. It's just something I'm doing that others have done. And that's all it is. It's geodetic triangulation. Maybe people aren't aware of it because we don't use it anymore, because we use GPS and GNSS pretty much to do everything. Total station instruments and angles and distances measurements are pretty small now, pretty short. They aren't many miles long anymore. All right, so these are the old days. Back in the old days, this is what it took to establish geodetic control in a region. And what you're looking at here is just a slice of a geodetic control diagram that covers the Lake Pontchartrain area, and all the triangles are control points. Normally, they are some type of a brass disc set in concrete or bedrock or something like that. And so it can be easily recovered, returned to, and used. All right. Now, you can get these diagrams for every state in the United States and some of the territories. And I'm sure you can get similar diagrams like these in Great Britain. I've gotten some from there. You can get them in Canada, Australia. You can get them all over the world. In fact, here's a map showing the control that was established for building the bridge, the causeway, across Lake Pontchartrain. You can read these for yourself. I won't stop. You could pause here to read these. Now, once the control is established, it's then used to make maps. In other words, once you have latitude, longitudes, and elevations on these control points, you can then locate other features like buildings, roads, radio towers, water towers. Anything that's visible has been intersected by triangulation to put them on maps. Now, here is the navigation chart. It's a nautical chart covering Lake Pontchartrain. You can get these charts for all the waterways around, you can get these for really around the world. Some of my other videos cover these charts and the use of these charts. Let me zoom in a little bit. On the borders of the chart are the latitudes and longitudes. And you can see here, you can see water tanks, you can see basically anything that could be seen from the water to use as navigation aids. Here's the southern end of the map showing the causeway where it touches, and you can see New Orleans here. Now, of course, these nautical charts do not contain all the details and the topography. It's really a map made just for navigation in the waterways. But you can see anything sticking up high is shown. Spires, stacks, smokestacks. There's the airport shown. And all of these rivers, all of these banks of rivers, everything has been located by survey methods. Now here's a topographic map where the details are greater. Okay, you're going to see all the stuff inland. And so basically where I'm going with this is that the same methodology used to produce all the maps and charts that you take for granted. I mean, look, your smartphone has smart maps in there. You can navigate your way to anywhere. And the base of those maps is from surveying done long ago. Today, this is all done by aerial methods and satellite imagery, but back in the old days, everything had to be located physically by a surveyor. So with that background, I will then, begin to show you how I did the triangulation to locate the Marriott building, to compute the latitudes, longitudes, and elevations of the corners and the red lights on the top. And here I am occupying a point LP1, and here I am occupying the other point LP2. So the theodolite is set over that, and the angles are measured. And what I'll do here is insert a video clip of me reading the horizontal angles and the zenith angles to some of the points on the building.
Point M1, roof corner. '85, 1848, the zenith angle, 276, 0615. I'm going to go to M2, the red light. Horizontal, 85, 37, 37, zenith angle, 276, 11, 38.
All right, so what I'm showing you here is a shot, picture through the telescope showing you one of the building corners that I called M5. And here is another view through the telescope with the crosshairs pointed on one of the red lights, and I called that one M4. When I was finished with all the triangulation, I made a posting to my Facebook group and let them know that that was done. Like I said, I periodically made postings to let people know how things were progressing. So now it was time to drive to the North Shore and get ready to observe the Marriott. It's a beautiful picture of sunset. It was a really clear night. It was a great time we had. This was a lot of fun, actually. Here's Soundly and me side by side working, and I think he's photographing planes. I think he's videoing planes landing in the water. If you haven't seen his video, you have to see that. The planes coming down and touching the horizon. And I'm occupying point LP3, which is the corner. I set a spike there at the corner of this concrete pad, which is a large foundation for what you see behind us. There's a giant windmill there. It's a cool photo. Here's just a picture of me measuring the height of the theodolite above the point. And now you're looking at a picture through the telescope with the crosshairs indicating the horizontal plane extended out across the lake. So what I'm telling you is that The Marriott building is 127,375 feet away. And the telescope is set to a zenith angle of 90. That means it is horizontal. And this is where the crosshair is intersecting the building. And I'll also show you a video clip of that. Just a little bit of calculating. The elevation of point LP3 is 7.15 feet. The height of the instrument above that point is 4.98 feet. That means that the crosshair is at elevation 12.13 feet. All right. There's just an outline of the building, and just to bring some perspective to what you're looking at, the elevation of that roof corner is 386.3 feet.
Zenith angle is 90 degrees, 00 minutes, 00 seconds.
Now, I stole this little image from Soundly's video called Blink Test Marriott. You should take a look at it, and you can see the minute mark where I took this from, where Soundly has put into the image the full building so that you can see the whole building, and you can see what is obscured by the horizon. Now, what I tried to do in my limited capabilities with this stuff is I just took a blurry image. Granted, this is me photographing through my telescope using a phone camera, but I'm just trying to show you that's what I could see, and you can see the horizon, that is the water surface, and you've already seen my crosshair coming through the building like this. So just to put it all together, and what are we talking about is the drop of the curve is measured down from that horizontal plane. The drop of the curve has nothing to do with the hidden distance or the hidden amount. It is really just a calculation of the drop down from the horizontal plane. And here it is. The drop of the curve down from the horizontal plane is 332 feet. And I'm using this formula, which is the formula for curvature and refraction that is used in surveying. And it's 0.57 feet times the miles squared. You'll get a larger number if you use the 8 inches times the miles squared. And here's just another posting I made to the Facebook group Flat Earth Can't Geodesy, letting everyone know we finished the work for that night. Things went really well. Soundly captured a lot of amazing imagery and video. I returned the next day. This is the auto level now, set up on the same point, LP3. And I'm making another posting to the group showing you the crosshairs over the Causeway Bridge at the end there. And you can see the Marriott building. I made a video too, a continuous, uninterrupted video showing you as I pan to the left. You can go and see the video. I pan to the left all the way to where the bridge is near to us at LP3. on the North Shore. And you can see that we are below the bridge. And then I pan back to the right, and you can watch the huts that are above the crosshairs. You can watch them descend below the crosshairs until you can see very far out there the huts are below the crosshairs, and you can also see the Marriott building. I then panned to the right to show you that this horizontal tangent plane is parallel to the horizon all the way out. And I even went further in this video to purposely tilt the level upwards and to show you what happens to the crosshair as you pan to the right. It starts to descend to a point that it eventually will intersect with the horizon. Anyway, that's what I did there. Here again, you can see the building. Just a little sketch to show you where it is. So here's what we see all the time. Show me the curve. Show me the curve. Where's the curve? It's right in front of your eyes. Just open your eyes. Now, you can go and look at these curvature charts that people have put out there using AutoCAD and everything. Here, I just grabbed one of them. And I've made videos in the past. You can go look at them about the flat Earth curvature confusion. They're so confused, mixing up the calculations from the drop of the curve down from the horizontal plane. They're mixing that up with the hidden distance over the horizon. And even when they do calculate the drop of the curve using 8 inches times the miles squared, they never establish the horizontal line, as you see, tangent to at the top of this curve. That horizontal line going out is part of the geometry that is necessary. If you don't have that geometry established, the formula is meaningless, okay? So I've shown you the drop of the curve. I want to start getting people to think about this angle right here. This is on these curve charts too. It's the theta angle. And that is the arc between 2 points, okay? 2 points. Point 1 has a latitude and longitude, and the other point 2 has a latitude and a longitude. The difference between those two is an arc. And this isn't simply a calculation, it's measurable. I can measure that, okay? Let's talk a little bit about this. When you see people talking about the 8 inches times the miles squared, and then they talk about how you shouldn't be able to see that thing way out in the distance, they're confusing two things. They're using 8 inches times the miles squared, but they think that they're calculating the hidden part over the horizon. That's a different calculation, okay? It's completely different. If you're talking about 8 inches times the miles squared, you are talking about this x distance that is measured down from the horizontal plane. You have to establish the horizontal plane if you're talking about 8 inches times the miles squared. Okay? Without that geometry, the formula is meaningless. And I've shown you in lots and lots of videos and photography through my telescope, I've shown you the drop of the curve from the horizontal plane. What I want to do now is focus on this. And I want to bring people's awareness up, make them aware of this theta angle. That doesn't get discussed much. What is it? It's the difference in latitude and longitude between 2 points. If you have the latitude and longitude for one point and you're looking out in the distance to another point, that point has a latitude and longitude also. And the difference between those two latitudes and longitudes is this angle. It's an arc. So I'm going to show you that. Now, here's one of the last ones I did across the Delaware Bay. You're looking at the Cape May Lighthouse from across the Delaware Bay on the Delaware side, looking towards New Jersey to Cape May Lighthouse. It's about 15 miles across. My telescope crosshair is at elevation 20. And in that 15 miles, you could calculate the drop of the curve using the 8 inches times the mile squared, about 158 feet. So you got to ask yourself, how is it that my elevation of 20 is touching the top of a 150 some foot building, lighthouse, right? So there's your whole drop of the curve business. Also in my little sketch here, you see on the left, the visual line of sight. I can see the lighthouse. It's not hidden. I mean, that's just stupid talk. I could see the lighthouse. Don't tell me it should be hidden. Don't tell me there's missing curvature. There's the lighthouse. I see it. I can see it. If you want to talk about the drop of the curve, you have to establish the horizontal tangent plane. All right, that's a whole different thing. Now let's talk about this theta on the curvature chart. If I have the latitude of where I am, and I have the latitude and longitude, I should say that over again. If I have the latitude and longitude where I am, and I know what the latitude and longitude is of whatever I'm looking at out in the distance, whether it's a mountain, a building, whatever, I can compute the arc that exists there, okay? There is an arc there. And in this case, it's about 13 minutes. Now I'm going to show you the Marriott building. This is for real. This is not made up. You're looking at this. And if you don't see it, you don't want to see it. It's just something you don't want to see. You want to see the curvature. You say you want to see the curve. Where's the curve? I'm showing it to you right here. There it is. That horizontal crosshair is at elevation 12. The Marriott roof corner is about 386 feet. I'm slicing through the building. Right? I'm not down at elevation 12 on that building, right? All right. So this is for real. What's the curvature? It's about 21 minutes. It's around 21 minutes. The drop of the curve using the 8 inches times the mile squared is 390 feet. That's without refraction. I already showed you the calculation using the 0.57. So this is 24 miles across, and the arc between the two positions of latitude and longitude come up to be about 21 minutes. So take your flat Earth game and, raise it up a bit. Go to level 7 or 10 or something. Now, if you don't want to get involved with a lot of involved calculations, all right, in-depth calculations, you can roughly approximate this. You can just take Google Earth latitudes and longitudes, use decimal degrees, it's easier. This is sort of like the Pythagorean theorem. That's all we're doing here is making a little triangle. It's not exact, but I'll tell you what, it's good enough for understanding this curvature arc, the theta angle from where you are to some other object out in the distance. So I've just tabulated this. I've got LP3 and M6, the latitudes and longitudes in decimal. And I find the difference in latitude, find the difference in longitude, square those and sum those, and take the square root. That's the approximate arc in decimal degrees. It comes out to be about 23 minutes. Close enough, Then comes the question everyone's asking, why can't I see the tilt? Well, isn't that supposed to be tilted away? Well, this is important for you to start to visualize this. Look at this. Can you see 23 minutes? You can't. And I say this to people all the time. If the picture in your living room was tilted by a whole degree. And that would be in like 60 miles in what we're talking about here. You know, around 60 miles gets to be about a degree. You can't see that tilt on a picture frame on your wall. So stop asking to see the tilt. You can't see it. And besides, it's tilted away. Yes, it's tilted, but you can't see that. So go get this book and start reading it. I'm going to start reading it on my channel for people. I really like this. Get this book. This is, you know, you're talking about all this stuff that's secret and hidden. The thing that's secret and hidden from you is the history of how we did things long ago and how we measured the earth. You just don't know about it. So go read about it. Start reading this book and find out about the hardships endured by people climbing mountains. I mean, clearing the tops of mountains so that they could see, and set up huge surveying instruments like, 5 feet in diameter. These are huge telescopes and huge circles to do astronomy. They had to establish latitude and longitude wherever they went in order to perform the surveying that they did. They had to measure the baselines using wooden rods. They didn't, this is before electronics. We have it made today. We don't even think about these things. They had to go and lay end to end these wooden rods to measure a baseline. And they had to measure a very long baseline, 5 to 10 or more miles long, for it to be of any value. And where did they do it? Well, they chose a long stretch of river. And how are you going to measure on a river? You got to wait till it's frozen. So they didn't go when it's warm. They go to these places when it's frozen, and they're out there measuring. Okay. Anyway, get this book. It's downloadable. It's a PDF. It's written in 1906, and start to open your eyes and think about how things were done in the past. And that's it. I'm going to leave that there. And the last slide, I think, is just my Facebook group, Flat Earth Can't Geodesy, where I stay in touch with it pretty much on a daily basis. And I have Flat Earth to thank for piquing my curiosity to see if I could actually see the curvature. Like I said, surveyors, we don't really think about this. Surveyors take it for granted that the Earth's curved. And most of the projects that we work on are projected onto a mapping projection called state plane coordinates. So we don't go out looking for the curve. But the flat Earth got me interested. I thought, you know what? I want to go see where can I see the curve? Maybe I can. And the first place I went was up onto Apple Pie Hill, up on the fire tower up there, and brought my instrument up there and looked at the city of Philadelphia, which you could see right up here in the top right corner. And, that was a wow moment. Like, oh, so that's what it looks like, you see. All right. This has been fun. I'm enjoying this. I sure do appreciate the comments and appreciate people subscribing as you are. I think I'll wrap this up. Look forward to the comments, and I guess the next video will be on Little Tensas Bayou and what we did there and the results we got. And I'm really enjoying seeing what Soundly's putting out there with his photography and good stuff. He makes great videos. All right. Thanks, everybody. And we'll talk to you all again soon. All right. So take care. Good night.